Hey everybody, Chris McClure here. We moved to the next section of Chapter 3 now that we have some experience in properties of functions and graphs of functions. Now we're now going to look at some basic functions that form kind of like the skeleton of many other functions. That's why we call it the library of functions, and we'll also take a look at some piecewise defined functions, which basically means that we bring together different segments of other functions to make one larger function, kind of like a Frankenstein function. You'll see it, okay? And make sure that you have your graphing calculator out, okay? And I'll show you how to do some keystrokes, how to graph some functions here in the library. Okay, so our first function right out the chute here is the square root function. We have the square root of x. Some basic properties of the function. Of course, we cannot take the square root of a negative number, and the square root is always going to be non-negative. So, as you can imagine, the domain is going to consist of all the non-negative real numbers, and the range is going to be the same, the set of all non-negative real numbers. And if you wanted to plot the square root function, square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, and so forth. So it's going to come up and start leveling off the larger the values of x are. But the value of the function is always going to be increasing the larger x becomes. Now, this function is neither an even nor an odd function because, well, the square root of negative x just doesn't exist, so there's really no symmetry to talk about. This function is always an increasing function, also on the interval from 0 to infinity. This function has an absolute minimum right here at the origin, 0, 0. All right, so square root function is a very common function. The fourth root, sixth root, eighth root, all those even index roots have similar behavior. All right, now on your graphing calculator, let's go ahead and pull up the graphing calculator. Let's see here. Pull up my graphing calculator, and we'll go ahead and graph the square root function here together. So go into the equation editor and just hit second and then this button right here to pull up the square root function, and then select x, and that's it. Now on the viewing window, well, we could set x to go from -1 to say, sorry, so there's -1 here, enter, to +9, enter, maybe by 2's. And then y minimum, let that maybe be -1, enter, y max. Well, we know that the square root of 9 is 3, so we'll leave y max. Actually, let's put y max at 4, enter. And the y scale could remain at 1. And then let's go ahead and graph. And boom, we see the nice square root function, that the graph of it right there. Okay. So I'll let you play around with that. Let's move on to the cube root function. All right, so I have some questions for you. First of all, can you decide whether the cube root function is an even or an odd or none of the above? Well, here's the hint. Replace x by -x, and what do you get? What is the cube root of -x? Well, the cube root of -x is is the cube root of -1 times x. And if we know that the cube root of -1 is 1, so you'll get negative of cube root of x. So you'll see that f of -x is the same as negative of f of x. So that means that it's going to be odd. So what does that say about the symmetry of the graph? So you should see that the graph is going to be symmetric because of the fact that the function is odd. It's going to be symmetric with respect to the origin. Okay. What intercept would you expect to see? Well, replace x by 0, and you'll have the function being equal to 0. So the one and only intercept is going to be right through the origin, 0, comma 0. And then, of course, we'll take a look at the graph of it. All right. And so if we want to graph by hand, we can specify some different values for x. Here's some different values for x right here. All of these values of x are perfect cubes. So when we take the cube root of them, you get these numbers right here. Except for the 2. The 2's not a cubic root, but we can take the cube root, I'm sorry, 2 is not a perfect cube, I should say. But if you take the cubic root of 2, that's about 1.26. So we could plot that. So we could plot these points, and what do we get? And here's what the graph looks like. Now for these points right here, those points are in the first quadrant, so we just plot them right there. And then because of the symmetry with respect to the origin, we can go ahead and graph the function in the third quadrant as well. So what is the domain? What's the range? Well, the domain is going to be from negative to positive infinity. Basically, you can take the cube root of any real number, and out's going to come some real number, either negative or positive. The cube root of a negative number is going to be a negative number. Cube root of a positive number is positive. Cube root of 0 is 0. All right, so there's the graph of the cube root. So here are the answers to the questions that we had on the previous slide, basically restating what I just told you. The domain and range are the set of all real numbers. The x-intercept is 0, and so is the y-intercept. Graph is symmetric with respect to the origin because of the oddness of the function. The function is increasing everywhere. For as long as x is increasing in value, the function is increasing in value as well. And the function does not have any local minima nor any local maxima. Okay, no surprises there. Now, if you wanted to graph the cube root function, no problem. So let's go ahead and pull up our graphing calculator. Go back into the equation editor. Go ahead and clear that. Hit the clear button. Now, I'll show you where to get your cube root button. Go into Math menu and go down within the Math submenu. And you see there's 4 submenus. Select the Math submenu. Hit option number 4. And then plug in X. And hit enter. Now, in the window here, maybe we could let X go from, say, I don't know, negative, oops, I better be careful here. Got to use this negative sign. I want to use the keys on my keyboard here. Negative 27. That's X minimum. X maximum, let that be positive 27. Enter. And we can go by 3s on the x-axis. How about, well, okay, that's good. Y minimum, well, look, we know that the cube root of 27 is 3, right? So we could let y minimum be, say, negative 4. And y maximum be positive 4, and y scale be 4, be 1, I mean. So then let's go ahead and graph. And there's a nice picture of the graph of the cube root function. Now I want you to carefully note the shape of this graph, because we're going to see the cube function here in a few minutes. And you're going to notice that the cube function is eerily similar if you were to rotate your calculator sideways. It's like, oh, that looks familiar. In fact, the graph of the cube root function is just like the graph of the cube function because they happen to be basically inverse functions of each other. And later in the semester, we'll talk about the relationships between functions and their inverses with respect to their graphs, okay? All right, now let's talk about our next function, the absolute value function. Now, we know what it means to take the absolute value of a number. Well, we can just take the absolute value of any number x. And there it is. There's that function. First question I have for you, is this function an even or an odd function or none of the above? None of the above? Yes? No? Maybe? Well, again, all you have to do is replace x by negative x. See what you get. Now, what's the absolute value of negative x? That's the same thing as the absolute value of negative 1 times x. And of course, you know that the absolute value of negative 1 is 1, giving you just the absolute value of x. So f of negative x is f of x. That means that the function is even. Okay, so whatever the graph is in the first quadrant, you'll have that same graph reflected about the y-axis in the second quadrant, mirror image. Intercepts, well, replace x by 0, and you'll get the function being equal to 0 as well, because the absolute value of 0 is 0. So there's only one intercept for this graph, and it's at the origin. And then we'll go ahead and graph this function as well. So here are some points that we can plot some different values for x, and of course the absolute value of these numbers is the same as the numbers. So we got these points to plot, and there it is, and then we can reflect that straight line across the y-axis. So you've got this nice V-shaped graph of the absolute value function. Let me show you on the graphing calculator how to graph the absolute value function. Go into your equation editor. Let's go ahead and clear this out. And then go into your math menu and right arrow over to the number submenu and select the first option where it says ABS open parenthesis. That means absolute value of. And just input x right there. Enter. Now go into your viewing window. Let x maximum be, say, I don't know, -5. X maximum, after you hit enter, x maximum be 5, enter. X scale 1, enter. Y minimum, let's let that be -1 so we can see it just a little bit below the x-axis. And then y maximum, let that be 6. And we'll keep the y scale at 1 as well. And go ahead and graph. And there's the beautiful graph of the absolute value function. Okay, V for victory. All right. Now, here are the properties that we were asking about from the previous page. The domain and the range. Well, the domain is going to be all real numbers. You can take the absolute value of any real number. But the absolute value is always going to be either positive or 0. And of course, you only get 0 when you take the absolute value of 0 itself. The absolute value of any other real number is going to be positive. So the range is always going to be the non-negative real numbers. So here's the domain, all real numbers, the range, set of non-negative numbers, non-negative real numbers. Remember, this notation in here in parentheses, or in the curly braces, that's set builder notation that basically says y such that y is a non-negative number. Intercept is at 0, 0. The graph is symmetric with respect to the y-axis because the function is even. The function is decreasing on the interval from -infinity to 0, and then beyond 0 to the right, from 0 to infinity, the function is increasing. Okay? The function has an absolute minimum at 0, 0. Okay, moving on here. So graph the functions listed in the library of functions. All right, so we already took a look at the square root function, the cube root function, absolute value function, but there are many other common functions like the constant function, where you have f of x is equal to some real number, b. For example, f of x equals 0, f of x equals -2, f of x equals pi, f of x equals square root of 2, whatever. And the graph is going to be a nice horizontal line, of course, with the y-intercept being that number that the function is always going to be. It's a constant function because regardless of what x is, the function's value is always going to be the same, whatever b is. Okay? Here's the identity function, which is basically f of x equals x. Why call it the identity function? Because what you put in is exactly what comes out. So f of -3 is -3. F of 2 is 2. F of pi over 3 is pi over 3. F of whatever is whatever. F of, strawberry milkshake is strawberry milkshake. Whatever. That's why we call it the identity function. The graph, of course, is the graph of y equals x. All right, it's the line that goes right through the origin. Has a slope of 1. All right, identity function. Then we have the square function, f of x equals x squared, which takes your input number and squares it. So f of 0 is 0, f of 1 is 1 squared, which is 1, f of -2 is, -2 squared, which is 4, and so forth. And here's what the function looks like. The domain is going to be all real numbers, but the range is non-negative real numbers for the same reasons as for the square root or the absolute value function. There's the cube function, which basically takes your input number and cubes it. So f of 0 is 0 cubed, which is 0. F of 1 is 1 cubed, which is 1. F of 2 is 2 cubed, which is 8. So f of 2 is 8. F of 3 is 27. F of 4 is 64. So you can see that it grows very, very quickly. So you only need to get out to like 5 or 6, and the value of the cubic function is very large as it is. And also in the negative sense. Remember, the cube function is an odd function. So the graph and function's behavior that you see in the first quadrant will be reflected in the third quadrant. All right, here's our square root function. We already talked about that. Cube root function. The reciprocal function will basically take whatever number that you're putting in and taking the reciprocal of it. So f of 2 is 1/2, f of 3 is 1/3, f of 4 is 1/4, f of 2/3 is 3/2, f of 0 is undefined, because you cannot divide by 0. Otherwise, you could take the reciprocal of any other number except for 0. Of course, the reciprocal of a very small number is going to give you a very large number. If you don't believe me, take the reciprocal of, say, 1/millionth, and the answer, of course, is 1,000,000. The reciprocal of a negative number is a positive number, so the reciprocal of -1,000,000th is -1,000,000. Remember, the reciprocal of 1 is 1, reciprocal of -1 is -1. So forth. So this is what the graph of the reciprocal function looks like. There's 2 branches of it. By the way, if you've ever heard of a hyperbola, well, this is an example of a hyperbola. We've got more to say about hyperbolas later in the semester, maybe, if we get that far. If not, you'll see it in a future course probably. All right, here's our absolute value function. We already talked about that. Here's another function. This function you may have never heard of. And it's called the greatest integer function. And this is what it looks like. F of x equals int of x. Never mind that asterisk. But it's sometimes called the floor function. But basically what it does, it takes whatever number that you're taking this function of and strips off whatever decimal might be following the whole integer part. So for example, 1.23. So f of 1.23 will just be 1 because the decimal part just gets poof, or the fractional part just gets truncated off, giving you just that integer. Now, of course, the int of 1 is 1, the int of 2 is 2, the int of 2.9999 is 2. Everybody see? So if you want to plot this, you can come up with some different values for x. And here are the corresponding functional values. The int of -1 is -1, int of -1/2 is -1. Because it's always going to output the integer to the left. So when you're between -1 and 0, well, the output is going to be -1, which is the nearest integer to the left. Okay, so the int of -1/4 is -1. Int of -1 1/4 would be -2. And of course, the int of all these fractions are going to be 0. So let's go and plot those. And boom, here is the graph. Let's see what this looks like on our graphing calculator. Pull up my grandpa glasses here. Go into your equation editor and your graphing calculator and clear out that absolute value function. Go into your math menu and let's hunt around for the absolute function. Not the absolute, but the integer part function. Now you could use ipart or int, and it's going to do the same thing for you. But let's go ahead and take the int function, int function, of x. Close parentheses. Integer. And I want to go from -10 to +10, -10 to +10, and we could do that actually pretty quickly just by going over to Zoom up here and then selecting the 6th option, which is the standard option. So that's going to give us from negative to +10, -10, +10. Of course, you don't see a whole lot of resolution, but you can see that stair-step being action. If you want to go from, say, -4 to +4 in the window, we could do that as well. And same thing for the y values from -4 to +4. So here's what the graph looks like. Of course, the graphing calculator is not going to show you the little the solid circle there and the little empty circle there, for example, but you have to understand that for yourself. Otherwise, here's a good graph of that integer function, greatest integer function, otherwise known as the floor function. All right, so become familiar with the integer, or the greatest integer function. Know how to use it. All right, there's another graph of it. Now let's talk about piecewise defined functions. These are our Franken functions, where you can just pull together some two or more different functions and put them together. And it's not like this is just theoretically interesting and with no practical applications. We actually have some real life examples where these things are used. Like, for example, have you ever had a service where the rate that you pay depends on how much you use? Like, imagine telephone service where you pay, say, 10 cents per minute for the first 400 minutes and then 12 cents per minute for every minute after 400 minutes, for example. Or if you have a rental car and maybe they charge you 10 cents per mile for the first 200 miles and 15 cents per mile for every mile after that, or whatever. Those are piecewise defined functions. So here is what it looks like algebraically to have a piecewise defined function. So we have the algebraic definition of the function for each different interval of x. So when x is greater than or equal to -1 but less than +1, then the function is given by -x plus 1. But if x is equal to 1, then the function's value is equal to 2. And if x is greater than 1, then the function's value is given by x squared. So what would be f of 0 here? Well, 0 for x is going to put you in this range here. So you'll just use this definition. Plug in 0 for x and you get 1. So f of 0 is 1. What about 1? What is f of 1? The answer is, because we're right here, f of 1 is 2. What would be f of 2? Well, 2 is greater than 1, so you'd have 2 squared, which is 4. F of 2 is 4, for example. That's how you would evaluate your piecewise defined function. What is the domain of this function? Well, to answer that question, let's start off up here. X is greater than or equal to -1. Okay, so that would be the left endpoint of the set of domain values for x. And it goes all the way to positive infinity as you work your way down. So x will go to positive infinity. So between -1 and positive infinity, that would be the domain. Let's go ahead and graph it. And I'll show you how to graph it using the graphing calculator. Okay. So this is what it would look like if you were to graph it by hand. You would graph the -x plus 1 line, which is this one right here. But only, you could use dashed lines to graph the line, but you would use the solid line just on this range of values for x, -1 to +1. But you would place a little open circle right down here at this end that corresponds to the fact that x is less than 1. But when x is equal to 1, we're at y equals 2 here. Okay? Then for x greater than 1, we have x squared. And that's this blue curve right here. So what would this look like on your graphing calculator? Well, I'm glad that you asked. So I'll show you how you do it. And this is actually a little bit confusing, so I'll go through it a little bit slowly here. We're going to have to put this in 3 different pieces. Let's go ahead and clear. Now let's go ahead and open up with parentheses, do an open parentheses, and plug in -x plus 1, close parentheses, and then do an open parentheses. And so we want to go from -1 to +1. But unfortunately, with the graphing calculator, we cannot use a compound inequality. So what we'll do is we'll just go, first of all, use the test function, so saying that x is greater than or equal to -1. So we'll go -1, and then go to test, and then choose option 6 for less than or equal to. And then select x, Now close parentheses and open parentheses again. And now let's do x greater than 1. X, and then go into your test menu again and select greater than, which is option 3. And hit enter. I know that's a crazy way to do this, but we are trying to tell the calculator that between -1 and +1, the function is given by -x plus 1. But the calculator does not know how to handle a compound or double inequality. Also at y2, the function's value is going to be 2, but when x is equal to 1, right? So how do we put that in? So we'll do the open parentheses like I just did, and select x. Where do we get equal sign from? Go into your test menu and select the equal symbol by hitting option 1. And then put in 1, close parenthesis, enter. And finally, let's do x squared. So x squared. And then in open parentheses, we're going to do x greater than, hit option 3 there, 1, close parentheses. Let's go to our viewing window. And we're going to let x go from, say, -2 to maybe option 5. Y minimum, maybe -1. Y maximum, I don't know, call it 10 or something. Enter. So if we did this right, looks like we didn't do this right, and that's okay. I could live with it. I think that we need to go back into the equation editor and double check we need for this one to be less than, not greater than, but less than 1. So let's change that to be less than 1. So that's option 5 there. Enter. And let's see if that fixed it. So yes, indeed. Now, the graph is not going to show that little dot indicating that the function is equal to 2 when x equals 1. It's just not going to show it. But when you go to the table, let's go to table set. And let's just have the table start off at, I don't know, maybe -2. And delta table being 1. And then auto, that's good. Go over to table now. And notice indeed that at -1, the function is equal to 2. In fact, let's go back over to table setup. And let's do delta table being, say, 0.1. Enter. And maybe we could have the table start off at -1. -1. Enter. And now go back into the table menu and take a look at the action of this function. And for this piece right here, that's your -x plus 1 function happening until we get down to x equals 1. And now we're here at where the function is equal to 2. Okay. And then for x greater than 1, then we're in the domain of y sub 3 there. And so all those x values are being squared. Okay, everybody see how that goes? All right, good stuff. So now you know how to input and graph your piecewise function in your graphing calculator. So what is the domain of this function? Well, is it ever going to be 0? The answer is no. It'll get close to 0, but it's never going to get down to 0. But the range is going to be all positive values for y. Okay, it's never going to be negative, never going to be 0, but just for positive values of real numbers. Okay, now let's talk about an example here. Let's read through this. In May 2006, we have this electric company that supplies electricity to houses for a monthly service charge, $7.58 per month. That's a fixed cost, plus 8.275 cents per kilowatt hour for the first 400 kilowatt hours used. And then 6.208 cents per kilowatt hours for all usage over 400 kilometers, or kilowatt hours. Okay. So let's go ahead and take a look at the graph, what the graph looks like right here. Starting off with 758, and we are going up at a slope of 8.275 cents per kilowatt hours. On the horizontal, we've got number of kilowatt hours used. So it shouldn't be a surprise that the slope of this little line segment here is the 8.275. Notice also on the horizontal, or on the vertical, I mean, we've got dollars, as in the cost that is being charged to us, until we get to 400 kilowatt hours. And then we see the changeover. After 400 kilowatt hours, then we're going up, meaning the cost is going up at a rate of 6.208 cents per kilowatt hour. So what would be the charge for using, say, 300 kilowatt hours per month? Well, it's going to be 758 plus 8.275 cents times the 300 kilowatt hours. So whatever, 300 times 8.275, and then move the decimal place over to make it into dollars, and then add $7.58. And that's going to be your charge in dollars. So that works out to be $32.41. Would be how much that you'd pay for using 300 kilowatt hours. Now, what about 700 kilowatt hours? How much would you get charged? Well, so first of all, you'd have to figure out what the charge is for 400 kilowatt hours, because that's going to be your $7.58 plus 8.275 times 400, and that works out to be $40.68. And then you have to tack on, for the additional 300 kilowatt hours, the 300 times 6.208 cents. Move the decimal point over, and then add that to the 4068. And the final answer is 5930. So I challenge you to work it out on your pencil and paper to verify these numbers. So this is an example of piecewise defined function. Any questions? And I think that there's a worked out example in the textbook anyway, if you really want to look at there's more detail. So I got a question for you. So take a look at this graph. What function is this the graph of? Is it the square root function? Nope. Square function? No. Cube function? Or is it cube root? Well, because of the fact that it goes from the lower left to the upper right and it's odd, or it's symmetric with respect to the origin, that means that the function that it's the graph of is going to be an odd function. And the answer is cube. The cube root function is more horizontally oriented. It does go from the lower left to the upper right, but it's more horizontally oriented. Cube root function is more vertically oriented. So yep, the answer is cube. All right, I've got another question for you. See this function right here? It's piecewise defined function. Which one of these is the graph? I'll let you take a look at it, and I'll give you a couple seconds to locate the graph. So as you're staring through there, just take a look at this first function. When x is less than 2, the graph is going to be a line with a negative slope. So that automatically eliminates options A and C, because to the left of 2 for this option A and for option C, those line segments are positive slopes, have positive slopes. So we'll eliminate A and C. So it's now down between B and D. So here's the next one. To the right of 2, the line 2x minus 3, that has a slope of 2. Now this line segment looks like it has more of a slope of 1, versus this one looks like it has more of a slope of 2. So I'm leaning toward B, but here's the clincher. What is the function's value at x equals 2? Now, at x equals 2, we'll use this piece right here, and you have 2 times 2, which is 4, minus 3 is 1. Not negative 1, but positive 1. So that corresponds to this point right there. And there we go. It's going to be option B. This right here is the graph of this piecewise defined function. And I challenge you to graph this on your graphing calculator. Try it and let me know if you have any questions. By the way, if you are interested in seeing more video of graphing piecewise defined functions, there are videos out there on YouTube. Okay? So that's it for today. We're going to look at transformations tomorrow. All right, well, have a good day, everybody, and I will see you next time. Bye.